All right, number 14. The radius of a sphere is increasing at a rate of 2 feet per minute. Okay, so they've used some keywords here. They said rate, and this is talking about the radius. So when you see the word rate, that means dt. And since we're talking about the radius, that means dr dt. So dr dt is 2 feet per minute. That means how fast the radius is changing. We want to know how fast is the volume changing when r equals 3. Okay, so we have an equation that relates the volume to the radius of a sphere. So if you have an equation that relates all of your variables, in this case radius and volume, you can go ahead and take the derivative. Because we're looking at how fast, once again, this is dt, the volume is changing. So dv dt is what we're looking for. Okay, here we have volume equals 4/3 pi r cubed. dv dt, taking the derivative of the left, is equal to, this is a number, pi is a number, the only variable we have here is r, it's the only thing that's changing. So it's r cubed, I'm going to bring down the 3. The 4/3 pi is still there. I'm going to bring down the 3. R squared, I just took dr dt. Okay, if you see the 4/3 and the 3 cancel, right? We want dv dt when r equals 3, so we've got pi. We still have our 4 up front. We have 3, because r is now 3 squared. And dr dt, they told us, is 2. So let's just clean this up. We've got 4 times 3 squared. 4 times 9 is 36. And 36 times 2 is 72. So we have 72 pi. We got to give an actual unit measurement here. So its volume is cubic feet per, and they said up here, minute. All right, what dimensions would maximize the area of a rectangle with a perimeter of 24 feet? Okay, this is an optimization question. So this is related rates. And this one is optimization. The key way I know that is by looking at these words. Rate, that's a related rate. Maximize, that's an optimization word. So we want to maximize the area. I'm going to draw a picture. I always start out with a picture so I know what my variables are. I'm going to call the sides of the rectangle length, and I'm going to call them width. So my area, which is the one I want to maximize, is L times W. However, I cannot take this derivative with 2 variables. I need to get rid of one of them. And that's what the other equation is there for. So the perimeter, they told me, is 24 feet. And if I look at the perimeter here, distance around the outside, I'd have an L and another L, so I'd have 2 L's, and I'd have 2 W's. All right, it's up to you which one you solve for to get rid of the variable in the area equation. So I'm going to go ahead and make my life easier. I'm going to divide everything by 2, which you can do if you divide everything by 2. This makes 12 is L plus W. So I'm going to go ahead and say that L is 12 minus W. Let me use that in my area equation. My area is now 12 minus W times W. Distribute out that W. So I'm still looking at area. I have not taken a derivative. Now I can go ahead and take a derivative. A prime is equal to 12 minus 2W. We see 2 things. Is our derivative undefined? Nope, it's just a linear equation. So what happens when we set it equal to 0? Well, I get 12 is 2W, so W would have to be 6. In order to do these problems, I have to perform a check. So I'm going to put 6 on my number line. I'm going to check it in the derivative. So I'm going to check a number to the left and the right. I'm going to look at it, as I said, in my derivative right here. So let me plug in like 5. 12 minus 2 times 5, which is 10. That would be positive. Plug in a number bigger, like maybe 7. 12 minus 2 times 7, or 14. That would be negative. So right here, I go from positive to negative in the derivative, which makes this a max. Okay, so I'm good. So go ahead, I need to answer the actual questions. This one is asking me not for the area, but it's asking me for the dimensions. So if W is 6, let me go back to my original equation. L is 12 minus 6, so L is 6 also. All right, last question. Number 16. F of x is equal to 3x cubed minus 5x squared plus 2x plus 2. And they want us to graph it from -1 to 2. All right, this is our function analysis. So if we are going to graph this from -1 to 2, I'm going to kind of set up a little graph over here. I want to go from -1 to 2. Okay, I'm definitely going to want to know what's going on at -1 and 2, so I'm going to plug those values actually into the equation. So f of -1, just plugging it in, this is all for a, would be 3 times -1, so -3, minus 5 times 1, so minus 5. So far I'm at -8, plus 2 times -1, so -2. So I believe -3 minus 5 is -8, minus 2 is we're at -10, plus 2 on the end. The 2 and the -2 pretty much cancel each other out, so that's -8. So at -1, I'm down here 1, 2, 3, 4, 5, 6, 7, 8, down here at -8. -1, -8. All right, I want to know what's going on at 2, so let me plug this in, f of 2. So this is going to be 3 times 2 cubed, or 3 times 8, which I believe is 24, minus 5 times 2 squared. 2 squared is 4, so 5 times 4 is 20. So now I believe we're at 4, plus 2 times 2, so that would be plus 4. Where I believe we're now at 8, plus 2, plus another 2, so it looks like we're at 10. So at 2, we're up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got that point, 2, 10. Okay. Do I just connect these two? Definitely not. That's why you learned function analysis. So if I asked you to graph this, we'd go ahead, we'd take the derivative. So we'd say f prime of x is equal to 9x squared minus 10x plus 2. We'd go ahead and we'd set that equal to 0, and we find out what's going on in terms of what values of x give us, what values of x give us a max or a min. That's what we're looking for here. Factorable, let's look at this really quickly. We've got 3 times 2. 3 times 3 gives us 9. I'm not actually sure if this is factorable. We've got 6 plus another 3. That would give us a 9. I don't believe this is factorable. So we would need to go ahead and use our calculator to solve for zeros for this. If you go ahead and do that on your calculator, then we are looking at, I'm going to graph it. I'm just going to graph the actual function on my calculator. 3x cubed minus 5x squared plus 2x plus 2. I'm just looking at on like a regular Zoom 6 or regular window. I know that these values are in there. It looks like, yeah, it definitely doesn't have a real 0, and the maxes and mins are going to occur at some kind of interesting places. You probably would not have, doesn't look like you're going to have real zeros here. It looks something like this. My scale is definitely a little off. It looks a little skinnier than this on the actual graph. And like I said, the ones that you're going to have to graph, we'd have real numbers for you, not these imaginary roots, which is what you are going to get here. Okay, so for part B, we can do part B, however. Use the graph of f to estimate the values of c that guaranteed by the mean value theorem. Mean value theorem says if the function is continuous, which this function is, and differentiable, which this function is, then at some point in time the average rate of change will equal the instantaneous rate of change for some value of c. So the average rate of change here is f of b, so average rate of change would be f of 2 minus f of -1 over 2 minus -1, which in our case, f of 2 we just found out is 10, minus f of -1 is -8, over 2 minus -1, which becomes 2 plus 1, or 3. This becomes 18 over 3, which is 6. So we say the derivative, which is this that we have right up here, f prime of x, has to equal 6 for some value in our interval from -1 to 3. And they want us to use the graph to estimate it. Using the graph to estimate it is basically saying the secant line, where do we think that the secant line will have the same slope? I'm guessing somewhere maybe here. Who knows? This is kind of an approximation part. So let's finish up this. I'm going to bring the 6 over. So I've got 9x squared minus 10x. If I have subtracted 6, I actually get minus 4 equals 0. And then I'm going to go ahead and graph that. 9x squared minus 10x. Oop, and I typed in 3. 9x squared minus 10x minus 4. I'm going to graph that. It looks like I've got, once again, some imaginary numbers going on there. Okay, I am going to minus 10x plus 2. When does that equal 6? I'm going to do second calc. I'm going to find my intersection points right there. Oh, not this, not the intersection, the zeros. The zeros, so somewhere there, 0, somewhere in between. I get a value of x that is equal to -0.312. And then it looks like I get another value of x from 0 to 2, let's say. That is exactly at 2. All right, so we have these two answers. These two values are the values of c that make this derivative equal to 0.